there. This is Dr. May. Welcome back to my channel. In this video, we're going to be looking at exponential decay. And I've got a great problem here with some radioactive material, strontium, and we are given a function to represent the amount of this material that is left. So it's important. We're told that A with the little 0 is the initial amount, and A is the amount after a certain amount of time in years. So then notice my last statement here. Assume that a scientist has a sample of 800 grams. So that's going to be our initial amount. That's telling us with A with the little 0 is 800. Okay. So the question here is, A says, what is the decay rate? Okay, so the decay rate is the rate at which this object is slowly going away. And if I look at my formula, the decay rate is the term that has the E with it. And notice I excluded the T because the T is a time factor. So it is E to the negative 0.0244. Now that might not make a whole lot of sense, but let's put that into our Desmos graphing calculator and take a look really at what we're looking at. Now, the Desmos graphing calculator is a free online graphing calculator, and I've left the link in the description for you if you want to take a look at it. All right, friends. So this is our Desmos graphing calculator. I'm just going to type that E, and then I'm going to use an exponent. Shift 6 will get you into the exponent. Negative 0.0244. Okay. So I want you to see that this number is the decay rate. Okay. But it is written as a decimal. So if I want to convert that to a percentage, you can see that I would get around 97.6%. And notice I know this is decay because that's less than 100. If that rate were greater than 100, we wouldn't be talking about exponential decay. We'd be talking about exponential growth. So that's important, a key factor here when we're looking at exponential decay. So let's go back and take a look at the rest of our questions. All right, friends. So depending on the instructions you're looking at or asking you to round, you may want to convert those one or the other. Okay, so B then says, okay, how much of the radioactive material is left after 30 years? So this is really saying, okay, what is A when T is 30 years? So what we'll do is we'll take our formula, A of T. We'll use our A of 0 being 800, we were told. And then we have our E to the negative 0.0244. And then we're multiplying times 30. And again, this is where I want to use that Desmos graphing calculator. So let's go back there. We'll take a look at how we find this value. All right, let's type in our 800 E, go into your exponent, shift 6, negative 0.0244, and I want to do times 30. And you can see that I got 384.76, depending on what your instructions are asking you to round to. You'll need to make that decision on how to answer that based on the rounding. Okay, let's go back to our questions then. All right, so we'll next look at part C, which says, when will only 600 grams of strontium 90 be left? So this is saying, okay, if A of T is 600, then I want to know what T is because it's asking for when. So let's take a look at what our equation might look like. I've got 600 equals 800 E to the negative 0.0244 T. So a couple of ways that we can do this. We can solve this by hand. And let me do that first, and then we'll double check it on the calculator. So the first step here is I'm going to divide by the 800 on both sides. So I need to get that E by itself before I can do anything else. That gives me 0.75 over here. and I've got e to the negative 0.0244t. Next step, I've got to get rid of the e, and the way to do that is to take the natural log of both sides. So I've got the ln of 0.75, and when I take the ln with the e over here, that ln and that e just go away. And then last step is I want to get the t by itself, so I'm going to divide by the negative 0.0244. Notice that this negative 0.0244 is dividing the logarithm, not the 0.75. So that's going to change how I actually put it in my calculator. Let me show you how I do that. Okay, so I'm going to type in that ln, and I need a parentheses, 0.75, and close that parentheses. So you notice how I added the parentheses in there for the ln. Then I'm going to divide by the negative 0.0244. And this is telling me in years, it's going to take 11.79. Again, depending on your instructions, if it asked you to round to the nearest year, you would say 12. But this is how I type it in my Desmos graphing calculator to help me to actually calculate that. All right, let's go back to our questions one more time. All right, so we found that one to be 11.79 years. And so D, our final question says, what is the half-life of strontium-90? Now, half-life means how long does it take for only half of the radioactive material to be present? So if you remember from this problem, we were told that it started out with 800. So if we want to know when there's half left, then we want to know when there's 400 left. So we're really looking for when A of t is 400, and I'll put 400 in for A of t. We'll leave the A of 0 at 800, and I've got that e to the negative 0.0244t. Now I'm running out of a little bit of room here, but I'm going to follow the same process that I did with part C. I'm going to divide by that 800. This time it's going to give me 0.5 equal to that e to the negative 0.0244t. Again, I'm going to take that ln, or that natural log of both sides. Same process I'm using to solve for both part C and part D here. Then I'm going to divide by that negative 0.024. Let's go to the calculator so we can get a value for this one. All right, let's type in that ln one more time, and I'm going to use a parentheses to put in the 0.5. Close that parentheses, and then divide by the negative 0.0244. And you can see in this case that it will take about 28.41 years. So about 28 and a half years for there to be half of the material left. So again, half-life refers to how long will it take for half of the material to be left. All right, my friends, I hope this helps you with your exponential growth and decay. These questions are very specific, but very common to these types of questions. And I hope we address those here for you. All right, thanks, friends. Bye for now.